Okay, we're continuing on chapter 2. We're talking about measurements. And remember, as we talked about, whenever you take any type of measurement, there's always going to be some degree of uncertainty associated with that measurement. Again, the degree of uncertainty does depend on sort of the equipment that you're using. And we talked about really there's kind of two markings you always want to kind of look at when you're using a piece of equipment, kind of the large markings and the small markings. And remember that essentially, like we saw with, say, the ruler here, usually our large markings will actually have numbers associated with it. And in this case, this would be 1 centimeter. And usually the small markings obviously will not have numbers on them. They will be the markings kind of between those ones that do have numbers. And when we do count the small markings, we always start after the last large marking. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And again, in this case, we do have 10 small markings. And that tells us that each of the smaller markings represents zero point 0.1 centimeters. Once again, you get that by just dividing that by 10 to get you there. One of the things we did talk about is typically speaking, you can go to one more place to the right of the smallest marking. And again, in this particular case, if we're looking at this arrow, this would be 1.1, 1.2, 1.3, 1.4. So we are clearly 1.3 here. Again, as we talked about, these are sometimes referred to as all the certain numbers. But as we saw, there is some type of estimation. So again, you want to kind of think about, is that like half, more than half, less than half? And again, you would record another digit here, and that would be your first uncertain number, or sometimes referred to as the estimated number. And that would basically be your measurement. We can always take the smallest markings, divide it by 2, and that gives us plus or minus 0.05 centimeters. And here they do usually want you to sort of record that if you're taking some type of measurement. The nice thing about taking the smallest measurement and dividing it by 2 is if you are not sure how far you should take the original sort of measurement to, it will tell you. So in this case, obviously, we get 2 decimal places. So that is how far we should take our reading to. Um, any questions on that we talked about there? So we did some different examples, rulers, graduated cylinders. Remember, some pieces of equipment, like the burette that we talked about, the scale actually increases as you go down, and it does sort of empty out at the bottom. So remember that if you have something like this, for example, and as we also talked about, typically liquid in a glass sort of container will sort of make this meniscus, and we always read from the bottom of the meniscus. And in this case, that would be, this ballpark. Here, this would be 1 point something, as it's again increasing as you go down, not 2 point something. So you definitely want to make sure that you do read it correctly. Other couple of things we talked about in terms of measurements, anything that's digital, you should record all the numbers on it as it's important. As well, and you should always look at the scale because, again, even if it's maybe the same piece of equipment as somebody else, the scale on it may be different, and you want to make sure that you do that. Again, it's not always possible to go one more place to the right of the smallest marking, like we saw when we were looking at the graduated cylinder that went by 2s. So sometimes it can just go kind of the whole number. Any questions on measurements there? All right. So I don't think we did this one. I think we laid up somewhere around here. So why don't you do this one here? This is again is a burette. So based on what you got going on there, what should be the proper reported, along with sort of its tolerance or precision, if you will. Okay, so let's take a look. So once again, this is a burette. We're gonna fill from the top. It's gonna dispense out the bottom. We do want to kind of think of the scaling, so I'm just going to go below it so I don't kind of mess with where we're going to read. So obviously these two markings here are large markings. The difference between those is 30 and 40. So really in this case, our large markings is something like 10 milliliters in this case. Again, if we count sort of the smaller markings, we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 small markings. That means that each of our small markings really is 1 milliliter. Again, 10 divided by 10 gets you there. So if we come up here to sort of where our liquid is, it does appear that would be 20. Right here would be 21. And it does look like perhaps it's right on the 22 mark there, as we would want to perhaps read our bottom of our meniscus there. So we definitely would record 22. In this particular case, we do know that our smallest marking is 1 milliliter, which if we divide by 2, will give us a plus or minus 0.5 milliliters. And that does mean that we can take this to the first decimal place. And that means that we actually should record, well, right there what I'm writing, 22.0 milliliters plus or minus 0.5 milliliters. So it does look like D would be the winner here. That would give us all of our certain numbers, right? And our first uncertain number. And as we also talked about last time, when you do that in a measurement, that is basically what makes up significant figures, right? So again here, this particular guy would have 3 significant figures. It is that 0 at the end as the uncertain or estimated digit, where sort of the error sort of lies. Any questions on that one there? So speaking of significant figures, we talked about a second ago that again it does come from really measured numbers, and there are some rules when we count significant figures. So let's talk a little bit about that. The first rule is basically any non-zero will count as a significant figure. So when we start counting significant figures, we do go from left to right, and you really start counting your significant figures once you hit the very first non-zero. So you don't really start counting significant figures until left to right. You hit that very first non-zero, and that's when you should count. So here, obviously, we would go here and start counting. All of those are non-zeros, which means that this guy would have 4 significant figures. Now, the zeros are something that gives people a really hard time, and there's 3 types of zeros. The first type of zero is what is sometimes referred to as a leading zero. These are all the zeros that come left to right before you hit the first non-zero. So those are not going to be significant. So you could have as many zeros as you want. None of them will be significant until you hit the very first non-zero number. So if we look at this one here, starting left to right, not going to count, not going to count, not going to count. Right here is where we start counting our significant figures, and the 4 and the 9 would be significant. So this would have 2 significant figures in this case, the last 2. The uncertain digit would be the 9 in this case, or the estimated digit would be the 9. There are what are sometimes referred to as trapped zeros or captive zeros, and these are zeros that are between 2 non-zero numbers, and those are also going to be significant. So if you have any zeros that are trapped kind of between 2 non-zeros, going to be significant. So once again here, we would start counting right here at the 5. These zeros are trapped between 2 non-zero numbers, so that makes them significant. And the 4 at the end is a non-zero, which would make it significant as well. So this guy would have 4 significant figures. Lastly here, the one that probably gives people the difficult time is the trailing zeros. And it gives people a hard time because the trailing zeros are the zeros that really come at the end of a number. They can be significant or they may not be significant. So it's kind of a yes or no on that one. And what determines whether or not that the zeros at the end are significant is there a decimal point anywhere in the number? So the decimal point does not need to be near those zeros. It just needs to be somewhere in the number. And if there is a decimal point in the number, then the zeros at the end would be significant. If there is no decimal point anywhere written in the number, so this is one where we're not going to assume there's a decimal point or anything like that. It does actually has to be written in the number. Then there would not be significant if there was not one. So if we write 600 like this, starting here, that 6 is going to be significant. The 2 zeros at the end will not be significant in this case because there is no decimal point written in this number. And this would actually have one significant figure. As opposed to something like this, if we did put the decimal point right there at the end, we would start with the 6, which would be significant. These guys would be now significant because there is a decimal point written in the number. Once again, it does not need to be near it, but it would have 3 significant figures. Questions on that there? Now, if you had a number like 0.004320400300300, and we'll just say that's some type of measurement, who knows? How many significant figures would this number have? Let's see. I don't know. I was just writing, so let's get it together here. All right, so we'll go left to right here. So these zeros here, are they significant? They're not significant because, frankly, we're not going to start counting until we hit this number right here, which is our first non-zero left to right. Significant, significant. That's a 0 that's trapped, which makes it significant. That's a 4, that's significant. These zeros are trapped, which makes them significant. The 3 is significant. That does leave us the 2 zeros at the end. Are they significant? The answer is they are, because way over here, there is a actual decimal point written in it. It does not need to be near it. So that would make these 2 zeros significant. I lost track there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this actually would have 10 significant figures. If you could use some type of measurement that goes that many decimal places. Any questions on that there? Remember that we also talked about, I think, scientific notation, I believe. And scientific notation, when you do write it in scientific notation, all the numbers that come before the times 10 part is significant. So again, this would be 3 significant figures. All right. Now, remember that sometimes people think that the estimated digit or anything like that, or the uncertain digit, is always the last one written, and that is not always the case. It is the last significant figure that's on the paper, but it may not always be the last one written. An example of that, for example, is 12,000. How many significant figures would this guy have? 2? I would agree with you. So it does have 2. That's significant, that's significant. All these zeros here are not going to be significant because there's actually no decimal point written. That would mean the estimated or uncertain digit is which digit? It is actually the 2. Yeah, that is the uncertain digit or the estimated digit. That's why that's a pretty crappy measurement, because you're pretty much saying, I think it's 12,000, but it could be like 13,000 or 11,000. That's a pretty big room for it's somewhere in that ballpark, right? So it's not the greatest measurement. As opposed to if you wrote this 12,000 like this, how many significant figures would it have now? It would have 5, because with that decimal, all these zeros at the end are going to be significant. The uncertain digit now is right there, right at the end. And again, that's a much better measurement in the sense that you're saying, I think it's 12,000, but maybe it's like 12,001, or maybe it's like 11,999, right? So that error is now moved way over there and makes it a much better, obviously, measurement as well. So as we talked about when we did measurements, remember you do need to sort of preserve the proper number of significant figures based on the measurement and the equipment that you're using. You don't want to kind of lose significant figures because you are going to make your measurement a lot worse. Nor do you want to do the opposite, as we also talked about. You don't want to add extra significant figures or zeros because, again, you're basically saying my measurement is a lot better than it can be or should be based on the equipment. That's also the same thing here. The estimated digit on this guy would be the 6, which is essentially telling us, I think it's 600, but maybe it's 7, maybe it's 500. Any questions on that there? All right. Now, exact numbers. as we talked about maybe a little bit before, exact numbers are obtained by counting our non-measuring devices. So basically, if it's an exact number, one of the ways you could get it is, just simply you would count it. You're not going to do some type of experiment or any type of measurement to figure out. So the classic example is you have like some apples or something on the desk. You're just going to count how many apples you have, or you have apples in a bucket. Also, more commonly, how we come across sort of exact numbers are in definitions, like 1 inch is exactly 2.54 centimeters. There are, in 1 pound, 453.6 grams. Anything like 12 inches is 1 foot. Any type of definition is considered an exact number. The deal with exact numbers is they have really an unlimited number of significant figures. They could have as many as you want. That means that when we do calculations that involve exact numbers, we actually don't worry about their contribution to your answer because they could have as many significant figures as you want. So later on here, we're going to talk about doing calculations involving significant figures. And once again, you will kind of ignore their contribution. You will really look at only numbers that have significant figures, measure type numbers, in terms of how far you should take your answer to. By the way, these are a couple here that they do want you to know, right? So make sure you do know those guys. We'll take a look at another idea here, which is there is some cases, as we'll talk about, that the only way, for example, to actually let's do this number here. Sometimes the only way to give an answer and maintain the proper number of significant figures is to use scientific notation. So, for example, this one of the ways that we could do this is if we wanted two significant figures, or for example, if we wanted two significant figures, we would go here. We would look at this, and in terms of rounding, we would actually just drop, or not really, put these guys as zeros. So we definitely could go with 12,000 written like that, which would give us two significant figures. Or another way we could do that is scientific notation. 1, 2, 3, 4, and we could put it in scientific notation. So you do have some options sometimes, and sometimes you can do sort of decimal form, or you can do scientific notation. But occasionally you will come across a situation where if you need to give an answer to the proper number of significant figures, really the only way to kind of do it is scientific notation. As we talked about, you can kind of control the number of significant figures with scientific notation by changing what you got here. Again, if we needed 3, we could do that. Or if we needed 4, we could add another 0 and so forth. All right, so for this particular one, how many significant figures there are, let's take a look here. Coming through, we're not going to count these. This is where we should start counting. The 0 there is going to be significant because it is trapped between two non-zeros, and that would give us 3 significant figures, which would be these guys right here. This number should have how many significant figures? This should have... This number has, it does have 4, yes, and this is scientific notation. So once again, all those are going to be significant, and it would have 4 significant figures. That's also important for scientific notation because sometimes when people maybe do calculation or they're asked, for example, how many significant figures does this number have? A lot of times what people will do is take the number out of scientific notation and then just kind of give an answer, and sometimes they give the wrong answer. Um, you should always look at it how it's written in scientific notation, and that will tell you how many significant figures it is. You shouldn't like take it out of scientific notation. By the way, if you do take it out of scientific notation, it should not lose significant figures along the way. It will still maintain the same number of significant figures as it has when it's written in scientific notation. This guy here, we're going to go left to right. Those are all non-zeros, right? Which should give us 3 significant figures in this case. All of them would be significant. This would have how many significant figures? This would have just one, which would be the 1 in this particular case. Again, there is no decimal point written, which means the 0 at the end there is not going to be significant. Also means the uncertain or estimated digit in this case is also the 1, is where that is at. Lastly here, this one's got how many? It has, what do you think? It does have 4. Again, we're not going to count here. This is where we're going to start counting. That's going to be significant because it's trapped. That will be significant. This will be significant because there is a decimal point in the number, and that would get you 4 significant figures in this case. Any questions on any of those there? All right, so we talked a little bit about the difference between measured and exact numbers. Once again, measured numbers are obviously, as it sounds, concern some type of measurement. They will have a certain specific number of significant figures based on the equipment that is used. Obviously, exact will be counted or some type of definition. So again, just to run through these, 155 pounds, that would be something that would be measured. I'd have 3 significant figures. Again, if we have a basket with some apples, you're just going to simply count how many apples you have, which would make it an exact number, which could have unlimited number of significant figures. 1 kilogram is equal to 1,000 grams. That is, again, a definition or equality, and that would be an exact number. And the distance from Colorado to Texas there is 1,720 kilometers. That would definitely be a measured one. By the way, that 1,720 kilometers would have how many significant figures? It would have 3. The 0 again at the end there is not going to be significant in this case. That would be the uncertain number would be which number then? It would be the 2. Yeah, so that again is the last significant figure is where the uncertainty or estimation comes into play. Any questions on those there? So let's talk a little bit about rounding. We do follow sort of simple rounding. If the first digit is to be dropped is 4 or less, we do typically drop the numbers. If it is 5 or more, we look at the digit next to it and we basically round up. So if the digit next to the number we're going to round to is 5 or more, we look at it and then we round up. We do not want to do any weird rounding along the way. So we'll go our 13,333. And let's say we wanted 2 significant figures. The answer should be, what do we think? 13? Yeah. All right. 13,000. All right, let's see if there is a difference. This one has how many significant figures? 2. All right, that's good. This one has 2 significant figures. So they both have 2 significant figures, but there is a very big difference like in the meaning of those 2 numbers, right? So for example, if I owed you $13,333 and I said I'm going to pay you 2 significant figures, here's $13. You're probably not going to be very happy with me because there's a very big difference between $13, right, and $13,000. So although this does have 2 significant figures, you have now just changed the meaning of that number by lopping off those zeros right at the end. This guy over here has 2 significant figures and $13,333, and I give you $13,000. Maybe you're not so mad at me at that point. Maybe get the teacher discount or something like that. But essentially, it means the same thing. And you want to really be careful of that. And it happens a lot, especially in this class and other classes. People are sometimes really focused, which you should be, on giving your answer to the proper number of significant figures, that they kind of just start going extreme rounding just to get the sig figs. So you never want to round if it's going to change the meaning of the number. You do need to round in the proper way. And this is also what I was talking about earlier. You may come across a situation, for example, like this, where you do know I need two significant figures, but if I do that, I really are not giving me the right number, or I can't write it that way without changing the meaning of the number. Again, in that case, you would want to do something like scientific notation, where you could kind of control the number of significant figures and definitely write it that way. Any questions on that there? All right. All right, so here, if we take a look at this, we got two significant figures for each of these. So we're going to look at two significant figures, which would be here. We then would look at the 7, and again, in this case, we're going to round up because it is greater than 5, and that would take us to 36 meters in this case. Once again, here on the second, we would go to our second significant figure. We would look at the number next to it. In this particular case, that is a 2, which means technically we get rid of those numbers, but we cannot, like we just talked about, just drop them. Otherwise, we have now changed the meaning of the number. So again, here we do need to place the zeros in there to maintain the meaning of the number. By the way, does it matter? Can I put a decimal point at the end of that number? I could not, because if I do, now we will have 4 significant figures, right? So again, you want to be careful. Some cases, obviously like this, you need to kind of import some zeros to maintain the meaning, but you got to be careful with the decimals. Otherwise, you may change the meaning of significant figures, which you're not trying to do either. Here, we're going to go second significant figure would be there as we start counting there. Looking at that, it's a 2. In this particular case, we can just drop them. And in this case, that will give us 2 significant figures. In this case, if I put the zeros at the end, what happens? I now have 4 significant figures, right? So again, because they are trailing zeros at that point, and there is a decimal point. So although you wouldn't change the meaning of the number, you would change how many significant figures you have in that number. So again, these are things you want to kind of think about. Sometimes people get fancy with it and go, it looks more chemistry-like. You throw some zeros or something in there. Again, you got to be careful not to change either the meaning of the number or how many significant figures you have. Here at a 2, we're looking at the 8. We're going to round up. And again, here 1.3. Also, in this case, we would not want to put zeros after the 3 because that would increase the number of significant figures in this particular case. Any questions on any of those there? By the way, a reminder, calculator does not usually give you your answer to the right number of significant figures or sig figs and stuff like that, right? So don't use all the numbers on your calculator usually. Make sure when you're ready to give an answer, you do round it to the correct number of significant figures depending on what you are doing. All right, so speaking of that, let's talk about kind of the rules that we do for really all the math that you're going to come across. So one of the things that you'll do is either multiplying or dividing. And when we multiply or divide, the answer that we end up with should have the same number of significant figures as the number with the least number of significant figures. So the least number of significant figures in your calculation is how many significant figures your answer should have. So if we had something like 4.50 times 2.1, here we are multiplying. So we're going to look at sig figs. This would be 3 significant figures. This would be 2 significant figures. And that means that my answer should have 2 significant figures when I do it. Again, based on the least number of significant figures when you do a calculation. And on my calculator here, if I punch that in, I will end up with 9.45. That means I do need to come to here, look at this number, and we're going to round up. So 9.5 in this particular case should be my answer when it's all said and done. Now, that goes for multiplying and dividing. It's always the least number of significant figures. When we add and subtract, it is a little different in the sense that we are not looking at significant figures. But when we add and subtract, we are actually looking at decimal places. And it is also the smallest number of decimal places is what your answer should have. So if you have 4.52 plus 1.2 plus, we'll go 0.111. We'll give it the old out the calculator try here. All right. So here we're adding, and we're looking again, not at significant figures, but decimal places. So that is 2 decimal places. That is 1 decimal place. That is 3 decimal places. So the least number of decimal places is 1. Here we would look at the 3 and just drop it in this case. And 5.8 would be our number in this case. By the way, that has 1 decimal place, but how many significant figures does it have? It has 2 significant figures. And again, that's important. For example, if you were then going to take that number and like multiply it or divide it, so you got to switch back to, okay, and at that point, I got to look at significant figures and stuff like that. It is the least number of significant figures. It is the least number of decimal places because, frankly, your measurement is only as good, or your calculation really is only as good as your worst measurement. And obviously, the least number of sig figs, least number of decimal places is your worst measurement. And that's why we always look at the smallest. Any questions on that there? Now, if we were doing something where maybe multiple steps together, so for example, if I was going to do 42.1 times 0.3 divided by 4, 6, 7, 8. If you had some type of problem like this, usually rules of math operation is whatever's in the parentheses is typically what you would do first. And that we are multiplying, which means we would look at significant figures. So this would be 3 significant figures. This guy would be 1 significant figure. Essentially, if we were just to get an answer for the top part, we actually should have 1 significant figure for the top part based off of that 0.3 number. We then would technically be taking that 1 significant figure and dividing it by what's on the bottom. That would be 4 significant figures. And that means really in our case here, our answer should end up at 1 significant figure based on that. Now, let's talk a little bit about rounding and doing calculations. You probably should not round until you reach kind of the very end of your calculation. And that's because every time you round, especially if you're going to, for example, take that number and use it in another calculation, if you round a little bit here, and then you take it and get an answer, and then take that answer, do another calculation, round a little bit there. Every time you round, you're moving yourself further and further away from the correct answer. So it's really good to sort of keep a few digits, and if you're not sure, you could write in a couple of extra digits. Sometimes people put a little line over the digit where you're supposed to kind of stop, so you know, hey, that's sort of where I'm supposed to be. And then kind of round at the end. I personally, in most cases, just kind of keep rolling with my calculator with all the digits, and at the end, kind of clean it up into the right digits. So for example, if we did this, the top part, we would end up with 12.63 divided by 4, 6, 7, 8. Now, again, at this point, I would not, because I know I'm going to do one more math step here, I would not round this to like 10 or anything like that. Because again, that's going to give us a lot of rounding error in this case. So what I would actually do is take the whole number there and then divide it by 4, 6, 7, 8. And again, sometimes people will just kind of put a line over like, hey, that's kind of where I should end up with that top number, just to remind you. If you want to do that, you can. Then I would divide it by the bottom. And here I would get 0.002699872 on my calculator screen. At this point, I now know, okay, that was 1 significant figure. That is 4 significant figures. So technically, that's where I should end up. And that's usually a pretty good sort of rule of thumb. Try not to round to the end. Do you have to keep every single number in your calculator? You don't necessarily have to if you need to write it down, but you should keep a couple, 2 or 3 past where maybe you should have rounded. And that usually will prevent you from getting any type of rounding errors, in your calculation, stuff like that. But if you kind of hardcore round everyone at every step along the way in a multi-calculation thing, you will definitely be kind of far away from the right answer. Any questions on that there? Okay. So let me clear what I just scribbled on the screen, maybe. All right, so this is what we got on the screen there, 9.378. As a reminder, as I mentioned, we don't always get the right answer sig fig wise. What should this answer be if I was going to give it? This should be, it should be 9.4. We are multiplying here, so we got 3 significant figures and 2, which means our answer in this case should go to 2 significant figures, which would be here. We would look at the 7 and has to round up, and that would round us up to 9.4 in this particular case. If we have this one, where should we end up? We should end up at the 8, yeah. Here we are dividing, so that is 4 significant figures, that is 3 significant figures. That means 3 significant figures. Remember, we don't start counting to here. So right there is our third significant figure. We would look at the 2 next to it. In this case, we would need to drop those numbers because again, if we put zeros there, we now have way too many significant figures. So we would end up with 0.0758. This one should end up where? 20, was it? 29.1. So we are in this case adding, right? So we do need to switch from significant figures to decimal places. So in this case, 2 decimal places, 1 decimal place, 3 decimal places. So 1 decimal place is the least, which would take us here. Once again, we're just going to drop those numbers so we don't end up with too many significant figures. That is 29.1, which has 1 decimal place and 3 significant figures in this case, right? And lastly here, we're subtracting. This one should go to, we're going to again look at decimal places. So that is 4 decimal places. That is 1 decimal place, which means we should end up at 1 decimal place here. We would need to round because of the number next to it, and we would end up with 0.6. Any questions on that there? So again, important not to do extreme rounding, not to round too much there along the way if you're doing multiple steps. Again, good rule of thumb, just kind of keep track of the significant figures and then clean it up at the end. If you are doing multiple calculations, basically the last step that you do will determine where you should end up, but all the previous steps are important to know. How many like sig figs you have for that last step or how many decimal places you have for that last step. So you do have to kind of keep track of it all the way through your calculation. Any questions on calculations there? All right. Then we talked a little bit about this earlier, the prefixes that we use for units. And again, a reminder that the proper way to use these, again, is that's how much there is in the base unit to one of the prefix units. So if we looked at our kilo, which is 10 to the 3, once again, what that means is in 1 kilogram, which is our prefix unit, there is 10 to the 3 grams. All of these are 1 times 10 to the 3, 1 times 10 to the minus 2. So again, if you need to put it into your calculator, you would put it in obviously using scientific notation and your exponent button like I think we talked about last time. Remember, it doesn't matter the base unit. If I had 1 kilometer, that is 10 to the 3 meters. So it works the same no matter what the base unit is. And it's really that prefix. As we talked about last time, pretty much most all of these on the list you'll come across a lot, but definitely in here, we do tend to see kilo, centi, milli a lot. And some of these other ones do pop up occasionally. But you should know pretty much, as we talked about, I think in an earlier table, it looked like this. You should pretty much know these. You could either know the sort of scientific notation version of it, or you can know the meaning there in the middle, but you do need to know how to kind of go between prefixes. By the way, if you do have a prefix to prefix sort of conversion, you really should a lot of times go back to the base unit. and then go from the base unit to the next prefix. So for example, if I was doing, let's say I had 5.2 kilometers and I want to know how many centimeters that is. And a lot of times people will just try to like move decimals and all that kind of stuff. So what you want to do in terms of pathway to sort of get you there is you want to kind of perhaps go back to the base unit because you'll know this table hopefully, and you'll be able to kind of find all the conversions or know all the conversions that you need. So probably the best pathway here would go from kilometers to meters, which is the base unit, and then from meters out to centimeters. So for example, we're going to do that and look at our conversions as we just saw in 1 kilometer. There is 10 to the 3 meters. And obviously centi we're going to use, which is right there, and centi 10 to the minus 2. That would mean in 1 centimeter, there is 10 to the minus 2 meters. So these are really, as we'll talk about here, what are referred to as equalities. And equalities are basically two things that represent the same amount of something, but are on different sort of units or scales. And from any equality, you could write what is referred to as conversion factors. And conversion factors are really just fractions. So for example, I could say in 1 kilometer, there is 10 to the 3 meters, or in 10 to the 3 meters, there is 1 kilometer. It's really just a fraction where one goes on top and the other goes on the bottom, and you flip it around. For my other one there, I could go 1 centimeter over 10 to the minus 2 meters, which again is 1 times 10 to the minus 2 in scientific notation. Or you could go 10 to the minus 2 meters is 1 centimeters. So one of the important sort of calculations that we do, and we're going to talk about here coming up here in chemistry, is what is known as dimensional analysis. And when they say kind of show your work using dimensional analysis, or pretty much in most cases when they say show your work, this is essentially what they mean. And what is dimensional analysis? Dimensional analysis is essentially this. It is you find an equality. It gives you an opportunity to use 2 conversion factors. And basically dimensional analysis is basically just 2 math operations. It's either you're going to multiply or you're going to divide, and you're going to do both of them together. So the basic idea of dimensional analysis is fractions and opposites cancel, which means if there is a unit you want to get rid of, you need to put that exact same unit in the opposite location. So if that unit's up on top, you need to then put it on the bottom with your conversion factor so they cancel. And if that unit's on the bottom, you need to put it on top so that they cancel as well. So always opposites cancel. To show you how this works, for example, we'll start with what we want, and we're going to take my 5.2 kilometers. Now, although my 5.2 kilometers is not technically written as a fraction, you could kind of think of it like a fraction, right? And if it helps you, you could even put a 1 on the bottom there. And what that does is it shows us clearly now, if I was looking at the units of kilometers, is kilometers on top or bottom? Top. So if I want to get rid of kilometers, I need to go in the opposite location, which means I need to put kilometers on the bottom. So that means I should go to my conversion factors and find the one where kilometers are on the bottom. And that would be this one right here, right? So that is the one where it's on the bottom. I would then set it up and go 1 kilometer is 10 to the 3 meters. Now, when we set it up like this, what we are essentially doing in terms of math is this. Anything that's on the top gets multiplied. So anything up on top gets multiplied. Anything on the bottom always gets divided. And those are basically the only 2 operations you're going to do when you do this. Now, what happens in this particular case, because those 2 units, the kilometers are on top and kilometers are on the bottom, they will cancel each other out. And you may say, how do they cancel each other out? Because we are basically taking kilometers on top and dividing it by kilometers on the bottom if we just look at the units. And that essentially equals 1. It's the exact same thing that happens when you take 2 divided by 2, you end up with 1, right? 4 divided by 4, you end up with 1. If you have the same number on the top and bottom you're dividing, you get 1. They cancel each other out. Works the same way with units. You've got the same unit up on top and the same unit on the bottom you're dividing. They go away. Basically, they cancel each other out. Now, if I stopped right at this point, the units I'm in are what? What units are left? Meters, right? And because I set it up this way, I could clearly see meters are on top or bottom? Top, which means if I want to get rid of meters, I need to put it on the bottom, the opposite, which helps me very quickly decide which conversion factor I should use. On the bottom conversion factors, should I use the one on the left or should I use the one on the right to achieve that? To get rid of the meters, I would need to use the conversion factor on the left, yeah? Whoops. So we'll do that. Maybe move that back down. And I'm going to then use the one on the left, which will give me 10 to the minus 2 meters and 1 centimeters. Once again, if I look at my units, I got meters on top, I got meters on the bottom, which means they are going to cancel, yeah? And I am left with what unit? Which is exactly what I'm looking to get to, right? So if you're looking to solve for a unit and it's only one unit, that unit should end up on top by itself, yeah? If you're looking for 2 units, you should have the unit you need on top and the unit you need on the bottom there in the same spot. So this is what is known as dimensional analysis. We're still going to do math-wise the same thing. We're going to continue to multiply what's on the bottom and continue to divide what's on the bottom. I'm sorry, divide what's on the bottom, multiply what is on top there. So let's talk about how we put this in our calculator. Once again, when you see the 10 to the 3, that is 1 times 10 to the 3, which is scientific notation. Depending on your calculator, you can put it in exactly like that. Some calculators, you don't need to do the 1. You could just do, the exponent. But if you want to be safe, do the 1. The 10 to the minus 2 on the bottom is 1 times 10 to the minus 2. Math-wise, when you do something like this, I would multiply as many numbers as you want up on top, and then you should hit equals at the end. And I would come back and individually divide by the numbers on the bottom, and in between hit equals. In between each one you divide. And if you do that, you will always get the right number. What people sometimes do is they try to put all the numbers in at once, and if you don't put them in your calculator with proper parentheses, you will do the wrong math and get the wrong answers. So if you, for example, come through here, you can multiply as many numbers as you like, but just hit equals at the end. And then when you come back on the bottom there, you should divide by the first number, hit equals, divide by the second number, hit equals, however many you have, and you will always get the right answer rather than trying to put it all in there at once. So if we do this, this is basically 5.2 times 1 times 10 to the 3. I'm going to hit equals. I'm going to divide it by 1 times 10 to the minus 2. And that is going to give me, I'll just come up here in the middle, 5, 2, 1, 2, 3, 4. And these would be centimeters in this case. We could also do scientific notation. 5.2 times 10 to the 1, 2, 3, 4, 5 centimeters in this case. First off, any question on the calculation? What about significant figures here? All I do when I multiply and divide, when I do dimensional analysis, the only math that you ever do when you do this type of setup is multiplying and dividing, which means you should always look at significant figures. The deal is this number here has 2 significant figures. This is an exact number because it's a definition between meters and kilometers, so we don't have to worry about that. This here is also an exact number, which means we don't have to worry about that, which means we should worry about the original number, which was 5.2, that had 2 significant figures, hence 5.2 here, where we have 2 significant figures as well. So our significant figures on this one, because all we did is multiply and divide, is based off of our original number of 5.2 in this case. The other 2 there would be considered definitions and exact numbers. Any questions on that? Does make sense because centimeters is a smaller unit than kilometers, right? So you have a lot more smaller unit than you do in the bigger unit, right? So that makes sense as well. So this is really when they say show your work. that is what you're supposed to kind of show, not just move decimal places because A, you won't get credit, and B, most people screw up on that as well. Yeah. So it's always a good idea, like we did here, just take it back to the base unit and go from the base unit to the next prefix, and you always kind of get the right answer. Any questions on that one there? All right, while we had that up there. So as we talked about before, some important equalities. 1 meter is 100 centimeters. Again, you need to know. 1 meter is 1,000 millimeters, you should know. And in 1 centimeter, as we saw on the ruler, there are 10 millimeters. So again, these are common ones that you should know. Volume, 1 liter is 10 deciliters. I would definitely say our 1 liter is 1,000 milliliters. Definitely one you should know off of here. And I think we'll see it on the next slide. Yeah. And on the next slide, as we see here, and we talked about, I think last time, 1 milliliter is a cubic centimeter, or a cc. Remember that if you take any sort of length measurement in cubit, you essentially have a volume in a lot of cases. So again, centimeters cubed, meters cubed, decimeters cubed, those are all volume. This is what a liter equals. 1 decimeter cubed is equal to a liter. All right, so we talked about cc's, cubic centimeters. Again, we would want to read this correctly, by the way. How far can we take the reading on this particular graduated cylinder? Whole number, first decimal place, second decimal place, third decimal place. How far can I take it to? All right, you're not sure? Let's try it then. So let's just say we are like here, my really badly drawn meniscus right there. We'll go there. What should the reading be? Take a moment and record it to the proper number of digits in this case. Pretend that's a meniscus and it's kind of Ewing there. All right, so what do we think? What should it be? 80, what? 85? Okay. All right, so let's see. So we look at our scale here. This is 60, this is 70. So our big markings here, our large markings is 10 milliliters. In this case, there is 1, 2, 3, 4, and 5 markings, which means each of our small markings here is going to be actually 2 milliliters, which if we take this and divide by 2 tells us the best we could do is plus or minus, not that, plus or minus 1 milliliter in this case. So we are going to go to a whole number. So in this case, here would be 82. This would be 84. Right there would be 86. So correctly, 85 is the best we could do in this case. Again, as we talked about earlier, there's not enough room there to know where 82 ends and 83 starts, right? So our 85 starts, I'm sorry, 82, 84 ends and 86 starts there. So 85, our significant figures in this case would be two significant figures. Yeah. Uncertain number would be the 5. Yeah. Any questions on that there? All right. Oops. Speaking of mass measurements, 1 kilogram is 1,000 grams. Definitely should know 1 gram is 1,000 milligrams. 1 milligram is 1,000. By the way, that is micro. That is the symbol for micro. That is micrograms there as well. But I would say the first two for sure are ones we come across again a lot here that you should know. All right, so we're gonna get through that. So we just touched upon it, but let's officially talk about conversion factors and dimensional analysis. As I mentioned before, a conversion factor is an equality that can be basically written as a fraction, where one of the qualities basically is the numerator, the other one is the denominator. Again, an equality is two measurements that really basically represent the same amount of something. From any equality, you do have sort of an option of two conversion factors that you could write, like we did in that previous problem there. So again, for example, we know that 100 pennies equals $1, right? And it represents really the same amount of money you could pay in the drive-through with pennies, I suppose. They probably don't want you back in the drive-through, but you could also pay with dollars as well. Again, for this, we could have two conversion factors, 100 pennies up on top and $1 on the bottom, are obviously the flip of that. $1 is 100 pennies. Once again, will you use both conversion factors in a problem? The answer is no. Otherwise, you just undid your calculation. Again, you're going to want to choose the one, as we were just talking about, is opposite location, what you need to get rid of. So always kind of think that in mind. Here are some common equalities. Pretty much, let's just say know this because it has most of everything that you probably need to know, though, for this class. So we have 1 foot is equal to 12 inches. Definitely comes across a lot. 5,280 feet as a mile is something that comes around a lot. 4 cups in a quart, 2 pints in a quart, pound is 16 ounces. Here's some of our metric conversions: kilometers to meters, meters to millimeters, and our volume, our mass, and our time that we talked about. And these are our ones that cross over between metric and US measurements. 1 inch is exactly 2.5 centimeters. So that is an exact conversion. 1 meter is 39.4 inches. 1 kilometer is 6.621 miles. By the way, this does pop up a lot. So does this one a lot. 946 milliliters is 1 quart. 1 liter is 1.06 quarts. And they actually do want you to know, not that number there, but they want you to know this. 453.6 grams is 1 pound. So we'll put that one up here as well. So all of these guys you could write basically 2 conversion factors for. You use it for dimensional analysis. Let's talk about significant figures. So we talked about when we do calculations, we really want to look at either sig figs or decimal places, but what is considered an exact sort of number and what is considered a measured sort of conversion. So here's the deal. If you're doing any type of conversion factor or calculation that involves a US to US conversion, is considered exact, which means you do not need to worry about it in your calculation. You just sort of ignore his contribution to your answer. If you're doing any type of metric to metric conversion, it's considered an exact number, which means, again, you do not need to worry about it in your calculation. It is only when you get to the last column here that you should worry. Yeah, so you do need to look at these. When you cross over and do a metric to US conversion or equality, you do have to look at the significant figures, except for obviously the first one, which is considered an exact. And at this school, apparently they consider the bottom one an exact as well. So we'll go with it. 453.6 grams is 1 pound. So if you were using, for example, this conversion here, which is again English to metric or metric to English, that would give you basically these 2 options here. 946 milliliters is 1 quart, or 1 quart is 946 milliliters. If you use this in a calculation, you would need to look at the significant figures in this conversion factor. Now, in most cases, you will have this situation where one part of the conversion factor is 1, and we would not look at that number. So what the number we would look at is, for example, the top number here, and that would have 3 significant figures. So if you have to look at a conversion factor that crosses over from metric to English, you should look at the one that's not the one. You should look at the other number in terms of the significant figures, and that's what you would use. I will say that probably most cases, even if you have to look at a conversion factor like this and take the significant figures into account, in a lot of cases, it oftentimes is still the original numbers where you kind of end up with, but it can be one of these. Another place where you would have to consider, for example, a conversion that you use and the significant figures is if the conversion is something that is not like actual conversion. It's specific for the problem. Like, for example, they say you're driving 75 miles per hour. That's specific for that problem. Everybody doesn't always drive 75 miles per hour. So that is specific for that problem. You would look at the significant figures in that number. So anything that's sort of given to you that you use, like a conversion factor sort of from the problem and kind of specific to that problem, you would look at the significant figures in that. Any questions on that there? All right, so let's take a look at some of these. If we have an equality such as 1 mile is 5,280 feet, which again is one that pops up a lot, so you should know. We can write these two conversion factors. Again, we could write 5,280 feet over 1 mile. Our 1 mile is 5,280 feet. Again here, we would probably not need to worry too much about the numbers and then this conversion factor. If you were driving 65 miles per hour, something per something, in terms of units means a fraction. So basically, if you're going 65 miles per hour, that means you could go 65 miles in 1 hour. That's essentially what that means. Lock it in the cruise control and nobody's in front of you. Or you could do 1 hour is 65 miles. In the case, if you had this conversion factor in a problem, you probably would look at it in terms of its significant figures. And in this case, we would be looking at the 65, which would have two significant figures in this case. Again, this would not be an exact sort of conversion because obviously, again, maybe you drove faster than that to school today. Hopefully not, but maybe you did. If we have 91 octane and we filled up, $3.05 a gallon. Where is that? I need to go fill it up. But that was expensive, believe it or not, when I wrote it, by the way. That means that for every gallon of gas we pump, right, it's going to cost us $3.05. Or for $3.05, we could get a gallon of gas. Basically, there's the two conversions that we could get. Now, also a very common sort of thing that we come across in chemistry that sometimes helps us do problems is a lot of times we are given things in percentages. And a lot of times if you are given something in a percentage, the easy way to convert it into sort of a usable sort of number is to assume that you have 100 of it. And the reason you do that is because the number stays the same. So if you got 12% on your exam, you probably got 12 points out of 100, right? So the number stays the same. So in this case, if we have 12% body fat, we could say for every 12 kilograms of body fat and 100 kilograms of body mass, or we could flip it around 100 kilograms of body mass, there are 12 kilograms of body fat. We could also do more of an English sort of unit, pounds, 12 pounds of body fat over 100 pounds of body mass, or 100 pounds of body mass over 12 pounds of body fat. So percentages we come across a lot, and again, to turn them into sort of a usable conversion factor, you could assume that you have 100 of whatever it is. Again, you could assume as much as you want, but the number would change, so just keep the numbers the same, just assume 100, and it's a super easy way to kind of turn it into a conversion factor. All right, so as we talked about before, and we did in that example, problem solving dimensional analysis. Dimensional analysis, again, is throughout your chemistry career here, is typically how you need to show your work. Okay, so it is what we just did there before. It is using equalities, it is using conversion factors, and it's using that setup of kind of fractions and showing the units canceling out and what you're left with. So again, if we had unit A equals unit B, and we want to go from B to A, and maybe we're starting with 5 of B, we would set it up like we just did in a fraction sort of sense, 5B, actually I'll write unit B. Unit B. We will set it up as a fraction. Again, if it helps you, you don't necessarily have to put the 1 there at the beginning, but if it helps you visualize it, go for it and put the 1 there. So once again, this is our equality, which gives us our two conversion factors, unit A over unit B, or unit B over unit A, and we'll just assume there's one of each of these. 1 unit A equals 1 unit B. So once again, opposites to cancel. Unit B is up on top. We would want it on the bottom, so it cancels. 1 of unit A, 1 of unit B. Once again, we're going to multiply always what's on top and divide what's on the bottom. Unit B cancels, leaves us with 5 of unit A as our answer. So again, as I mentioned before, this is the setup for dimensional analysis. This is how you need to show your work. It's how you need to show your work, like in those calculation boxes in the lab, yeah, for those experiments and stuff like that, on tests, quizzes, all that type of stuff. Now, sometimes people are resistant to do this. Let me just give you a piece of advice. Don't be resistant to do that because you want all your points. But more importantly, as we get going through different chapters and we start getting formulas and stuff like that, there is a lot of problems that you could set up with dimensional analysis that frankly will allow you to not even have to worry about rearranging formulas or remembering formulas or just rearranging them, because that's where a lot of people screw up, is like rearranging formulas. They multiply when they should divide when they should multiply. They're not sure, what they should do. If you set it up with dimensional analysis like we do here, frankly, all you have to remember is what's on top gets multiplied, what's on the bottom gets divided, takes care of all the math for you. And secondly, all you have to remember is I don't want those units, but I want those units. So opposites cancel, and it will frankly do all the math and rearranging of formulas for you as we go through it if you set it up this way, rather than, okay, D is equal to M over V, so V is like M divided by D, and try to rearrange those things. So it's kind of like a no-brainer in the sense of if you set a majority of your problems up this way, essentially all you have to remember, like I said, opposites cancel, multiply top, divide the bottom, and you'll usually end up with the right answer without, again, having to necessarily rearrange formulas and stuff like that. So you definitely want to get into a habit of doing that. Here are the general steps to problem solving and really dimensional analysis. As I mentioned before, it's a really good idea to write what's given to you. You want to think about what you're trying to find. You also want to think about what is the pathway to get you there. Now, when you do these type of problems and you're doing really conversions, there could be multiple kind of ways you get there depending on what conversion factors you choose. But if you choose all legit ones, you should all end up in hopefully in the same spot at the end. You want to think about the equalities that get you there, the conversion factors. You should set up the problem to show the units canceling. And you should, again, also solve the problem to the proper number of significant figures, because, again, that also helps you with what you should do at the end. Because as I mentioned before, if you're doing dimensional analysis, you're only multiplying and dividing, which means it's all about significant figures all day in terms of your answer, and that's what you should end up with. So you don't have to worry about, should I look at decimal places here? Should I look at, significant figures? If you set it up this way, multiplying and dividing should go sig fig. So again, that helps you out with that. All right, we will lay it up there for